Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Cristina Dalle, who is a PI at the SETI Institute, and she also spends a lot of her time over at NASA Ames across the road. Cristina did her laurea in astronomy at Padua University, and then came across and did her PhD in astronomy and astrophysics at UC Santa Cruz. Her research revolves around the chemical distribution of the current solar system, and with the aim of determining its evolution. She's a spectroscopist, and she's particularly interested in bodies of the outer solar system, including the Saturnian satellites, as we're going to hear about today, and hydrocarbons or tholins that may be causing reddening on those icy surfaces. She's also interested in Kuiper belt objects and centaurs for what they can tell us about the dynamical evolution of the solar system. And she's also interested in spectroscopy of the asteroid belt. So today she's going to, in particular, talk to us about three objects that she's been looking at with Cassini data. So if you'll join me in welcoming Cristina.
Thank you, Adrian. I will be talking about and as you can see, the characterization of the dark materials on Iapetus, Phoebe, and Hyperion. And well, you will see. I want to give you a warning. It might be towards the end a little bit technical, so don't hesitate to stop me and ask questions. Don't be shy, because I actually like it a lot to make it more interactive. So, but before the show, we had the ads, and actually, this is no joke. The 2013 NASA budget will bring huge cuts, in particular to our planetary science. If you like what you've seen so far coming from Cassini, from Mars, from all those missions, and the projects that arise from them, you have to help us. And you can do that by writing to your representatives, and you can find sample letters at the website. That's, actually, is this working? Oh yeah. That's on the SETI Institute website. If you go to the SETI Institute website, there will be a page, Save Our Science, SOS, that will provide you with sample letters that please send to your representatives. So now, the show. Yes, I will tell you a little bit about Cassini and its mission to Saturn. And obviously, I will start with an introduction to the satellites, a very brief one, because I mostly will be talking to you today about one of the satellites, Iapetus. And I'll give you, a lot of facts, history, a lot of recent discoveries, and hopefully you walk away from here with a little bit of more knowledge. So don't get overwhelmed. And as I said, feel free to stop me and ask questions. At the end, I will present our latest results. And those are, in fact, the fruit of the research that I've been doing with Crukshank at NASA Ames. And that will be published in the near future. To start, the Cassini Mission. It's a wonderful mission because Cassini was launched in 1997. It took 7 years for it to reach Saturn. And in 2004, it started sending us data. And those include pictures, a lot of which you've seen probably on the website, as well as spectra, in my case, that I like to use because they tell me the story about what those pictures mean. and a variety of information. And with that, it's brought us discoveries that we would have never imagined about those worlds, the satellites of Saturn. So the Cassini mission was supposed to end in 2008. It's been extended twice. And this is another sign of how successful this mission is. So now to the Saturn satellites. The Saturn satellites, there are many satellites that orbit Saturn. You see here a comparison of sizes. Saturn is down here at the bottom, so it's huge. Now, the other satellites that you see here are the mid-sized satellites, Rhea, Dione, Thetis, Enceladus, Mimas, and Iapetus, and some of the small irregular ones like Phoebe and Hyperion that I will tell you more about. And I don't know why this moved, but I apologize. Back to the slide. I want to say another couple of things. These mid-sized satellites are really what Cassini has been exploring most because they're close to Saturn. There's also Iapetus that's a little bit further out, and Phoebe, and Hyperion, and Phoebe is the furthest of all. It has been observed only once when Cassini was arriving at Saturn. So while flying in, it kind of flew by Phoebe out here and took some very essential data that I will tell you about in a few minutes. So let's go on, and I hope, yeah. Iapetus is the main satellite that I want to tell you about. It was discovered in 1671 by Gian Domenico Cassini with a very small telescope, and still Cassini was able to discern about this satellite that it had an orbit that was about 80 days in length. It took the satellite 80 days to revolve, to orbit Saturn. You can see it here. But the other thing that he noticed was that the satellite was disappearing sort of halfway through its orbit. And this fact was interpreted correctly by Cassini as being due to the fact that Iapetus, in its orbit, it's locked and shows always the same side to Saturn. So while doing that, because now we know it has one side that's dark and one that's bright, when it's facing away, the bright side is facing away from us, and it shows the dark side to us, then it looks like it disappears. And Cassini was intrigued by this fact, but could not tell at the time anything else about this body. He didn't know if the body was in fact, that it is, as we know, dark on one side and bright on the other, or if it was just an effect due to the shape of the body that was elongated, for example. That could have also caused, if pointing to us its small side, it would have caused it to disappear. So this is what Cassini managed to do. It's okay, that's all right. So what's the matter with Iapetus? It took a long time before Dave Morrison, actually, and Dale Crukshank, who is sitting right here in front of us, managed to solve the conundrum. And it was through ground observations. Obviously, there was no Cassini mission at the time in 1975, but they were all able to observe the satellite and see that through its visible light, and by looking at its thermal emission, that the satellite was very bright in one position and cold, and was dark and warm. And based on this, they could tell that it had to be the surface covered by dark material, because the dark material, as we will see in a few minutes, tends to warm up. And so that's why the temperature difference. That gave it away for us. So that was a great discovery, and there were many more observations that came in the following years, including 2 Voyager flybys. But I'm going to jump to the latest news about the dark material. And there are, again, important news. Again, it was Crukshank et al. That in 2008 detected the polycyclic aromatic hydrocarbons in the dark material of Iapetus. This is the spectral signature that identifies, this is from the lab, and this is from Iapetus, and it identifies the material as being polycyclic aromatic. And what are those? Some of you might say. Well, nothing so fancy. I think the name is maybe one of the most difficult things, at least for me, to pronounce. But what they are, they're common. They're the product of combustion. And they're interesting to us because they tend to react with water, oxygen, and in UV light particularly. They can produce interesting, from the biological standpoint, interesting molecules. I show here the most common one, naphthalene, and the simplest of all. I mean, I should say not the most common, but the simplest of them, which is just made of 2 benzene rings, and it's the simplest of the polycyclic aromatic hydrocarbons. So, any questions? Am I losing people already? No? Okay. So this was one important discovery. The other very important discovery was done in 2009 by Verbiscer and her group of collaborators who, no, sorry about this, it didn't work. No, I apologize. This is not what I want. Okay. So, and Verbiscer, making use of, again, data from a spacecraft, a space telescope, the Spitzer's telescope in this case, was able to see that there was some thermal signal around Saturn. Now, let's look closely at this picture. You can see in the very center of it, this Saturn with its rings, you know, the big system of rings that we know. It's that little dot in the middle. Then you see Titan and its orbit, it's the first little ring, blue, around it. And it's starting to give you, I believe, an idea of how huge this ring is. Iapetus orbits a little bit farther out, it's the green orbit, and then the ring itself is orbiting along with Phoebe. Phoebe is that satellite that I was telling you about that was encountered by Cassini when he flew, arrived at Saturn. It's one of the outer satellites. Well, it looks as if the ring is traveling with Phoebe around Saturn. And it's thought that it might have been caused by a collision of Phoebe with maybe a comet or an object that caused a lot of its dust and material to just be sent into space, and it's now orbiting around Saturn at this far distance. Some of the ring particles, the smaller ones, tend to spiral down towards the planet. And that's how it's making the inside of the ring also kind of a little bit dustier. So now imagine we have Iapetus that is orbiting, and it happens to be orbiting in the opposite direction from the ring. So it encounters these particles even though they're very sparse. Imagine that if you were standing inside the ring, you wouldn't be aware of these particles being there, the dust being there. So it's sparse, but still it's been going around for years and years and years collecting these little particles. And like your car, when you're driving in a cloud of mosquitoes, if you want, you'll be collecting a bunch of them. And that's what has happened to Iapetus. And that's why this side of Iapetus is so dark. So, yes?
Does that ring have an alphabetic designation?
The ring, you know, not that I know of. I don't know what its denomination is. If somebody here in the audience knows, please let me know. But
the Phoebe ring.
That's what I've been calling it, but yes.
Are there any other satellites within the ring?
There are actually. Very good question, and thank you for reminding me of that. Yes, once, and I'll talk a little bit more in detail about this, but once past Iapetus, there is a Hyperion. And past that there is Titan, and then obviously the rest of the satellites. So it is presumed that the dust is also being partially collected by Hyperion.
You didn't mean to say Titan was beyond.
Well, closer to Saturn. Yeah.
It's away from the ring.
Yes, it's farther in. So now, another interesting piece of information. This comes from the theoretical side. There have been people trying to model what is the distribution of this dark material on the surface of Iapetus. And I have a little cartoon here that shows in time what might have happened, starting from before the ring was there, before this collision that could have caused it. There was just water ice on the surface of Iapetus, and we believe there was already some contamination from some dark material of some kind. Then the ring came, and there was infalling of this other dark material we call it exogenous, and now we know that it's coming from Phoebe, that mixed in with the native material. By doing so, it kind of made that side, as we know, darker. And by doing that, it raised the temperature on that side of Phoebe, which is what has been observed, in fact, by Morrison et al. In 1975. So the temperature on that side became higher. A higher temperature implies that the water ice that was there started sublimating and migrating, essentially, to places on the satellite that would be colder. And those were what? The trailing side, the side behind where there was less dark material. And therefore, the ice was colder. And so there was this segregation of materials. This effect that caused the back to be brighter, all the ice kept on going there, and the front was left with just this lag material, which is this dark material, exogenous and native, mixed on the front, very dark. So because of this model, we expect that this is the Spencer and Denk's model. Actually, what they predict is shown here in these two maps. There are two different models where they changed some of their parameters. It's interesting to see what the observations look like. You can see how amazingly similar they are to the model, confirming that what they're theorized is really happening. So we know that, there's another piece of information that I should give you for the history of this satellite. Another theoretical study done by Tamayo et al. More recently has shown that the dust particles that come from the ring, those particles that are between, say, a few microns to about 10 microns, tend to collect only on, or mostly on, Iapetus itself. The smaller particles, the very, very small particles, tend to escape from Iapetus and land on Hyperion. So, and this is again, theoretically, yes, it's a theoretical study, so it has not been observed yet.
Could you give us some sense of the temperatures that you're talking about?
Yes, between the two sides of Iapetus, we are ranging between 88, 90 degrees Kelvin on the cold side, and it can go up to about 130 on the dark side. So it's a fairly substantial difference. And because of this difference, by the way, I should say that one of the consequences is that there should be essentially no water left on the dark side. So anyway, Tamayo predicts that there should be quite a bit of dark material on Iapetus, a fairly thick layer, and made mostly of these 10 micron particles, and the smaller particles should be on Hyperion, coating it very, very lightly though. And the other thing that I should tell you about Hyperion is that it doesn't, unlike Iapetus, it's chaotic in its motion. So it's like, completely, or would be completely embedded in in the dust, on all sides. So you wouldn't see a very obvious effect as you see on Iapetus. Now, more facts about Iapetus. Denk et al. In 2010 showed, or noticed, I should say, a very subtle effect. And this is important because this is what I've been studying particularly. They noticed that the dark material on the leading side, which is what I've been telling you about, is different slightly in color from the dark material that's at the edge already on the trailing side. There's a slight difference in coloration. One is slightly redder than the other. And from this observation, Denk et al. Also said, well, it must be that one is exogenous and the other one is native, maybe. So this is one point, and I'm showing it again here on a 2D map of Iapetus. You have the dark, very dark leading side of Iapetus here, and the trailing that you see, it's the dark material is spread over it a little bit. It kind of wraps around a little bit, but it's already much less dense, and it includes probably some other dark material because of the different color. So what we know from either observations or some theoretical studies is that there are two kinds of material, exogenous and native, that they should be segregated, sort of. The exogenous should be obviously only on the leading side because that's what's coming from the ring. And they differ in color. We presume that there is no water in the dark regions. And we think that the dark material originates from Phoebe and lands on Iapetus and then Hyperion possibly. And that the same process, Tamayo says, could have happened before it happened for this ring. Yes. What, so I don't know. Okay. Yes.
Why shouldn't water be continuously generated if it's impinging the ring coming in? I mean, the dust coming in.
Okay, there is dust. The dust doesn't have water.
It doesn't have water at all.
No water on the dust. So it's just dust coming and and water escaping from the warm areas. So there is no replenishment because the temperature is too high.
Where did the water come from initially?
Well, it was there, we think, when the satellites formed. Okay.
My question, you mean the dark material originates from Phoebe or from that Phoebe ring that you talked about?
The Phoebe ring, but with
Phoebe ring.
Yeah, the Phoebe ring, though, it's pretty much, again, we'll try to demonstrate more of this, but it's thought that it has to come from Phoebe itself, because it's
Phoebe ring came from Phoebe, a collision with something. But
exactly.
These particles.
Well, obviously,
from
from the ring. Yeah, the ring has been the medium that has
Why
been.
isn't that leading edge and trailing edge? Wouldn't it be a straight line, like the first quarter of the moon?
Yeah, good question. Yeah, it wraps around, and I believe that has to do with the dynamics of the dust particles. And in fact, the Tamayo.
With the leading is the planetary, or the satellite dynamics such that it should be like the first quarter of the moon, a straight line.
It should be intuitively, but the dust has
Sort of
maybe.
swirl.
That's the way I picture it in my mind. Yes. So there is still a fair amount of material that needs to be proved because some of this is theoretically, predicted, and some of it has been observed but not really explained, and that's where we come in. And the data that we have at our disposal is the data from Cassini. We have been working with about 30 Cassini cubes for a total of 16,000 spectra, covering the wavelength range between the visible and the near infrared. And the cubes cover a total of the surface of Iapetus of about 700,000 square kilometers. Now, I want to give you an idea of what the data look like, because I'm talking here about surface as well as wavelengths. Each cube looks, I mean, this is a rendition, obviously, it's not the actual cube, and this actually is Jupiter. But each one of our cubes looks like a picture, say, of the surface that we're observing, a low resolution, lower than you see here, and each pixel of the picture is actually a spectrum, which is what you see here. It's very important for us to have the spectral information because that's where the signature of the different materials that make up the surface is contained. And that's how we can say this material is made of this or this or this. So we're dealing with about 16,000 spectra spread over the surface of Iapetus. So we need some tools to help us work with this. And the tools are a mosaicing tool, and the mosaicing you will see help us include the geographical information that's in the picture. And we also use a cluster analysis, and the cluster analysis is important because it helps us reduce, if you want, the number of spectra. I mean, if I were to study 16,000 spectra, I would be here until the end of my life, for sure. And I probably would have done, a few. So I'm reducing with this technique, it's a statistical technique, I reduce that huge number to a handful that I can deal with and I can analyze and understand. So let's go on. Here I show you the mosaicing, what it does. It's essentially like a collage of the cubes. It helps us put the cubes together. We have for each cube the geographical location, and we just stick them together, paste them together to create a mosaic. And the mosaic obviously corresponds, so we have the correspondence of the geography. We see where each cube goes, essentially what it's related to, what kind of surface, in this case the dark material and not as dark material around there. So it's very important. And the other important tool is the clustering. And here I have a precise definition of clustering, statistical definition, but what it boils down is that it's just a very simple-minded, useful tool. Not very different from sorting buttons. Here, making it more serious, I show spectra, very simple spectra. Say that this is a spectrum and this is another spectrum, the clustering, and they would be obviously intermingled and, mixed. On my surface, the clustering is able to discern which is which and put them all together and calculate an average that becomes the representative of all this cloud of spectra. The cloud of spectra are similar to their representative. Obviously, some of them might be slightly off, higher or lower, but the centroid is really the representative. So instead of having to study the thousands that you see there in the cloud, I study just the one that represents them. Here we see the actual data for Iapetus. Here is our mosaic, and you can see here in lower resolution that you can still discern where the dark material is, the dark areas, and where the bright material or brighter material is. Now, this is what I give in input to my clustering, and this is what I get in output. It's a color-coded map now. And I can already see that, for example, in this case, the blue corresponds to the brighter areas. And then when I go, the other output that I obtain from the clustering is the centroids, and the centroids are showing me the actual spectra for each one of those areas. The blue has these very big, deep features, bands, that you see here, and they are a sign of presence of water. So they're the water signature. You can see that water is present in the blue, the turquoise, yellow, orange, but it kind of disappears from the red and the purple. So we know that where the red and purple in the map, where they are located in the map, there's very little water, if any. And that's, in fact, the dark material. So here we have already a hint that it's true that most of the water is gone from those parts of the satellite. So what can we do spectroscopically? Can we identify the spectroscopic signature of the dark materials? the polycyclic aromatic hydrocarbons. And can we, through the signature of these materials, can we discern whether there are in fact two kinds of dark materials on Iapetus? And then can we compare them to the other satellites? Because if we find finally what the signature is, and we compare it to these other satellites, then we can say, yes, it's proven. It comes from Phoebe. Or, it's on Hyperion as well. So, but it has to be done very carefully because, as I was telling you before, the clustering tool that I use is very simple-minded. And it will discriminate among spectra based on the most apparent of its features. So it's not necessarily always what I want. What I'm looking at, what I'm looking for, is something that, okay, these are some sample spectra that I've been using, a centroid, say. And you see the range of all the little spectra, how they vary, but the centroid is what I work with, the dark line in the middle. And what's inside the green circles is the signature of the dark material, where I'm looking for it. And more precisely, let's look at an enlargement. What I'm looking at is variations of these very subtle inflections here. You see those little, very, very weak dips. They're here, here, and here. Those little inflections is what I'm looking for throughout the 16,000 spectra. It's a very challenging project. So the first step that I take is to use just the darkest of the spectra, the ones that I know have less water. I've already dumped out of the 16,000 all those that are farther out here that I know have water. So let's look at what has less water. And by doing my clustering, I obtain this first clustering. And when I look at the spectra, well, first of all, I want to show you something kind of cute. This enlargement refers to this area here. You can see that there is like a clump of blue pixels. Those pixels have a different signature, and look at it. They are still water rich. So what I personally believe is that we're looking at a spot where something has collided with Iapetus and has dug out the ice that's underneath, below the dark material that covers it. And that's why we see more ice in that particular little spot here. But let's concentrate with the other spectra. You can see that there is still a fair amount of water because we see a feature here and a feature here, also in the yellow and in the greenish. So these regions here are still affected, and it makes sense because they're so close to the water region. They're still affected by water, while really the purple and the red are what seem to be almost devoid completely of water. So what this is, this was a stumbling block for me because I stared at the spectra and I said, okay, but what is this telling me about the polycyclic aromatic hydrocarbons, the dark material? It's still just telling me where the water is. This is not what I want. And again, it's because the clustering is looking at the most obvious differences, if you want, between the spectra. What I'm looking at is this tiny inflection here. How am I going to make the code look at what I want and finally discern what I need? Well, I had to play a little trick. I extracted for the code the signature of the polycyclic aromatic hydrocarbons by doing a fit. Essentially, I fit with a spline the data, and this is a sample of them, and then I divide one by the other. And by doing this mathematical little trick, I obtain the features. These are the little features, the baby features that I'm looking for, these little things. And those are what I'm looking, that's where the signature is. And that's what's going to tell me ultimately the kind of material that I'm working with. So I clustered this extracted features, this, you know, the 6,000 whatever I had of this. And when I did this is what I got. I should say that for detailed reasons that I'm not going to bore you with, I clustered first focusing on this first part, that's the aromatic feature, to see if this changed and how it mapped. And this is what I obtained. And I want to go back and remind you what the aromatics are. The aromatics, what I call aromatics, is the polycyclic aromatic hydrocarbons, again, are these rings that you see here, a very simple example for. And what you produce when you barbecue your steak outside. So that's what the signature of that material is what I've been working with. And then I repeated the same analysis, the clustering, telling the code to look just at this feature and find me all the different kinds of this other little band. And I could find, the code found 3 kinds of it on the surface of Iapetus that are mapped here. So there is the teal and the red and the blue. And the blue and the red are more similar than the teal. So already here I'm starting to say, yes, there are for sure 2 kinds of dark material because they have a different signature, the teal and say the blue are definitely different. And they map because the blue and the red are mostly on the leading side, which is where the Phoebe material lands, while the teal is outside the range of the Phoebe material. So now it's time for me to look at the other satellites and where are Phoebe with respect to Iapetus and Hyperion, and what do I know about these satellites? Well, Phoebe, it's a very small satellite, and it's particularly interesting because it has a very different density compared to Iapetus and Hyperion. And its orbit is retrograde, it's inclined, eccentric, and people think that it's captured. It came from somewhere in the solar system, and in fact, most likely it came from the edge of the solar system. It's a Trans-Neptunian object, say similar to Pluto. So that's what Phoebe is, and that's the material that we're looking at on the surface of Iapetus, most likely. So what about Hyperion? Hyperion is also a small satellite, and it's also very interesting because its rotation is chaotic. As I was telling you before, it's like, you know, spinning while orbiting around Saturn. And its density is so low. So it's an intriguing body as well. Here we look at their position with respect to the planet. Again, Phoebe, it's the outermost, and then Iapetus and Hyperion. Titan is actually a little bit inward, but because it's also scrunched up here in this picture, it's hard to tell the actual distribution. So, as I was telling you, Phoebe is likely to be a captured Trans-Neptunian object, like this that we know of. These are the most famous, biggest ones. Obviously, we don't know how it happened to be captured by Saturn, but it's quite intriguing because it's one of those objects that there are thousands of them, but they're going to tell us a lot about the history and evolution of the solar system. So to have one so close that we can examine, it's already in itself a discovery. Again, one more of the Cassini discoveries for us, of its gifts. A picture of Phoebe, so that you have a close look at it. It's irregularly shaped and kind of rocky, looks like. This is the mosaic that I work with, and here are the results of the same analysis that I explained to you in detail for Iapetus. The same thing was done on Phoebe, and these are the spectra that I obtained. And they're kind of noisy a little bit, so it's not perfect, but life is not perfect. So here's a picture of Hyperion, the other satellite. And I should say that these pictures are from the astronomy picture of the day. And they're gorgeous pictures from Cassini, obviously. And look at Hyperion. As I said before, it has a very low density. And you can see it here. It looks like a sponge. But in that sponge, you can notice how there are regions that are lighter in color and darker. The sun cups are darker. They have they're like pits of dark material on Hyperion. So, yes.
But the idea was that the dark material would be evenly.
Absolutely true. But remember, it also said that the idea was that it would be very thin, less than a centimeter. Can we see it?
But if there was dark matter even that thin on the flat areas, wouldn't you see it?
Possibly, yes. But let me finish the story, because I have the next slide might partly answer what you're saying. Well, the next couple of slides. Here I have the analysis for Hyperion, and you can see that some of the dark materials, one of the spectra, the light green one, maps, you can see it best here, maps with the dark material on the surface. Where are we? The dark material maps with the light green here. So we are, in fact, looking at one of the signatures here that I have is for the dark material. And by isolating that and finally comparing with Iapetus, this is what I obtained. It turns out that the darkest material on Iapetus is similar to the noisy Phoebe data. This is unfortunately the only data that we have for Phoebe, and Cassini is not going to go out there again to take more. So we have to make do with what we have. But I think the results are very encouraging, and I believe that indeed we can say that we've proven that the Phoebe dark material is the same as the Iapetus dark material on the leading hemisphere, the one that plows through the disk, the Phoebe ring, the ring. But now let's look at the other material, the teal material on Iapetus. This material that's a little bit out of the darkest material. The teal trace compares best with the Hyperion dark material. So what I interpret from this is that Hyperion had some dark material already present on its surface, the way that Iapetus did. So what we call the native dark material on Iapetus is very similar and possibly the same as the native dark material on Hyperion. If there is trace of the Phoebe dark material on Hyperion, it's not sufficient to give us a clear signature. And this is something that I should look at more in detail. These are the latest results that I have. And to summarize, we confirm that there are at least two kinds of material on Iapetus. And we can say that they look like Phoebe, one of them, and Hyperion, the other one. So in order to infer if the Hyperion native material is the same as Iapetus, we need to do even a more detailed study of these spectra. And to do so, and possibly search even more to make sure to see if we can find any trace of the Phoebe material on Hyperion. But so far it doesn't look like. So the more detailed study that we are going to do in the near future consists in looking at the spectroscopic traces, de-convolving them by means of Gaussians, and obtaining the ratio of the different aliphatic and aromatic modes. And this is very technical, and I should maybe try to make more sense of it for you. The two bands, the two features, the aromatic and the aliphatic, seem to vary among the different kinds of dark material. And this is proven also by the fact that we have samples of polycyclic and aromatic hydrocarbons and aliphatics coming from carbonaceous meteorites micrometeorites. These were collected here on Earth. Interplanetary dust particles, also collected up in the atmosphere of our planet, as well as samples from a comet and interstellar dust. The interstellar dust signature is observed looking at stars and seeing the signature appear on the background of the star. So by comparing to all these signatures, we can tell if any is similar to what we see on Iapetus, and already we can say from our preliminary results, they seem to be different. This is very interesting, but it's also possible because, again, Phoebe comes from out there in the solar system. It's a totally different object from what we've been exposed to probably here on Earth. These meteorites, they might not be coming from the same source. That doesn't look like based on the spectral signature. So this is where I leave you right now, and that's all I know for the moment, but that's in the direction I'm going to. And to end my talk, I want to remind you, please, to go on the website and send a letter to the representatives and save our science. Thank you for your attention.
Cristina, could I kick off the questions with where does that dark Hyperion material actually come from then? Do you have is it on that APOD image where that spectra actually comes from? The Hyperion dark stuff. Is it in one of the craters or something like that?
It would be in one of the craters. The dark material would be from those darkest spots. The darkest spots is where...
And you don't have like a mosaic of Hyperion?
I cannot make a mosaic of Hyperion, unfortunately, because of its chaotic motion. I don't have the coordinates of the cubes. And so, we can't put, or I should say, I can make small mosaics, say, of cubes that were taken together on a flyby. Then I can make a small mosaic of those because I know what they refer to, and then by eye, I can try to match it, but there is no actual number that tells me this position corresponds to this on the surface because of that.
And just my final question is the Phoebe image that you have, or the Phoebe mosaic, seems to be off to the side of most of the dark material. Most of the dark material isn't actually captured. Is that going to be done in future Cassini flybys? Or?
Unfortunately.
Sorry, not Phoebe, the
Phoebe is what?
One. The Iapetus.
The Iapetus.
Images.
The Iapetus, we have more cubes, and I suppose, well, I don't know where the actual slide is with Iapetus. We have more cubes, and possibly we might be able to do more studies of the surface of Iapetus. Okay. Let me see if I can find it.
Yeah, this stuff.
There, yes. We have focused mostly on the dark stuff, but there is a wealth of information, again, more on the very, very, very dark. So we can repeat the same study on a slightly different part of the surface. Yeah.
How unusual is the low density of Hyperion that you mentioned, and is there any understanding of what caused that?
We think that, and Dale might be actually very good at answering this question because he knows a lot more than I do about the satellites, but it's probably not a captured satellite. Is that correct, Dale?
Hyperion?
Hyperion.
I have no idea why the rotation is chaotic. I don't think it's regarded as a captured satellite.
No.
Because it's in a prograde, more or less circular orbit. And
Chaotic motion is pretty well understood.
not by me.
Or by me.
But I'm asking about the density.
Oh, the density. Yeah, it's that is not known. There could have been a removal of a lot of the volatile material over the history of the Saturn system. It may represent another category of very low density objects that we're finding in the Kuiper belt, for example. It's not unique in that its density is less than 0.6. There are Kuiper belt objects that are. And to the other point that you mentioned earlier on, Jeff, Hyperion it's basically an icy porous body, but its overall reflectivity is only 30%. So all of that ice is dirty. Some of it slightly less dirty than the other, but it is, it's a darkish object.
Thank you, Dale. Yes. Oh. Sorry.
Can you show the comparison slide of the three different bodies again, and just try to say again what the subtleties are, the differences between the aromatic,
final one?
the aromatic and the aliphatic signatures?
Yeah, let me see if I can find it quickly.
Yeah, that one. Oops.
There. Okay. What we think, you can see the blue one is the Iapetus dark, the leading hemisphere dark material. And we look mostly at the aliphatics. And the reason for that is because we think that some of the aromatic feature might still be contaminated by water. So we look at this feature, and this feature looks very similar to the Phoebe noisy data. And for Hyperion, it's the same thing. We look at the aliphatics more than the aromatics for the same reason. And we see a similarity of the overall feature, even though maybe the overall depth is not the same, but it's, I believe, similar enough to justify it, possibility of being common in origin.
I have a microphone. Excuse me. I'm wondering, do they know how the PAHs are formed in space? I'm sure there aren't barbecues in Pretty sure. No barbecues, no aliens barbecuing hamburgers there. No, I agree with you. Well, there are different sources of energy that can produce, again, they're sensitive to UV light particularly. But now, your question is a very good one, because we still don't know, we're investigating what their origin is. Did they form in the solar nebula, say, when the solar system formed? Did they form in the outer parts of the solar system? Or, particularly because some of these organic, we call them organic materials, originate from irradiation of ices, and this has been shown in the lab. So would they be processed ices in the outer parts of the solar system? Could they come from the interstellar medium in the form of small grains that were, for some reason, saved throughout the process of the nebula, the formation of the solar system, and now here they come back again? We don't know. And we're still investigating all these questions and trying to, make sense of all of it.
I had two questions, actually. One of them pertains to the last question. It's not clear to me how you could go from carbon and hydrogen that would be blown out of a supernova to a hydrocarbon material.
I agree with you. I mean, you need, carbon and hydrogen. You need a source of energy. You need an ice that contains both. And you need irradiation at a certain, of some kind. Is that what you're asking? I'm not sure.
I think of the carbon as condensing as graphite, and I think of the hydrogen
That's actually the end state of this.
Of the supernova I'm talking about now, that would have been precursor to the formation of the solar system.
Okay. So you would have some carbon and some hydrogen.
Yeah, and there wouldn't be hydrocarbon from a supernova directly.
It would not.
Yeah.
It would form, say, as methane, for example, in some particular environment that would promote this.
You wonder what that environment would be, though.
It has to be cold enough. And again, Dale, I don't know if you have any more information about this, But I would say it cannot be a hot environment because methane, in fact, as a gas, will not, I mean, it's very volatile, so will not survive.
Yep. I'm going to get in a plug for a previous talk here. We just had a talk by Jan Camille, who's also at the SETI Institute, and he was talking on space buckyball. So check that out on YouTube, and that will possibly help with both ways.
The buckyballs are still elemental carbon. They're not hydrogen.
Yeah, well, that's right.
Yeah. I should say that once you bombard, for example, methane ice, then you start having the production of these organic materials that look like a dark tar-like material. The more, and it's reddish to start, the more you bombard it and the more you go back to the carbon, you lose the hydrogens, essentially. The hydrogen gets peeled out and you go back to graphite eventually. So it's an evolution. It goes from the ice, you start irradiating, it becomes reddish because of this material, and then it becomes slowly dark, black.
Yeah, well, it clearly happens.
Yes,
There's
it
a
does.
lot of methane.
And we see a lot of all of these throughout the solar system.
My other question was about the ice.
Yes.
It's water ice. But it's not cold enough to involve methane or ammonia.
Yeah, correct.
Okay.
On the Saturn satellites, that's the case.
All of this about the origins of carbon-hydrogen bonds and all brings up the question of equilibrium. And what do we know about, at these temperatures, 10K, 50K, 100K, whether or not we are at chemical or chemical equilibrium in these systems? Does anyone know what the condition is from that perspective?
Boy, Dale, can you answer this question? I'm not sure I understand it.
Because, well, just, if certainly mixtures of hydrogen and carbon, for example, at some conditions, thermodynamically will
Are not
generate,
stable.
relative to hydrocarbons that are formed. And it depends upon partial pressures and temperatures and all. But so are these systems at equilibrium over the very, very long periods of time that you're considering or not? Does anyone know?
I don't know. Well, certainly there's someone knows. Actually,
there's a whole field of effort out there dealing with interstellar chemistry and the reactions that are possible in various sorts of scenario. And I think the answer at these temperatures, no, there's no chemical equilibrium. This is not thermodynamic equilibrium.
So slow, even over.
The calculations have been done. You need several, depending on the system, I mean exactly what you're talking about and the fine details. But by and large, you do not get equilibrium in these sorts of reactions in the lifetimes of the solar system. So these typically are kinetically controlled reactions. They're occurring in, as I say, a variety of environments in the interstellar medium. There are textbooks on this. It came out in the 80s, I'm sorry. But yeah, there's an entire reaction sequence with every element in the periodic table going through this kinetically controlled process, and coming out of it are several hundred different molecules, all of which, some are in this astronomical environment and some are favored in this astronomical environment. There's no difficulty making hydrocarbons and PAHs and this sort of thing through non-equilibrium, kinetically controlled reactions. And there's a whole suite of different types of reactions. Iron molecule reactions, I know, are very, very favored for a lot of isotopic properties that you see in these primitive materials.
Yeah,
it's a whole different universe of
I would like
science.
to point out the fact they're not closed systems. I mean, there's energy that's being supplied
Right.
not only by the sun, the cosmic rays, but also the dust itself is delivering energy. Each particle, when it hits the surface, is delivering a little bit of energy. And even that little amount of energy could be sufficient to maintain a state of non-equilibrium.
In the case of the organics in meteorites, then that's right. The surface catalyzed reactions are very important. The kinetically controlled reactions, they're not.
Are those if they're catalyzed, are they equilibrium?
No. You don't get chemical equilibrium until you start to get to these thermodynamic models for forming the solar system when you're within a few AU of the sun, and even those are sort of a little suspect. But
Thank you, Derek.
At the beginning, you cited a couple of papers by an author who made some predictions about how some of these materials are transferred from moon to moon.
To Maya.
And you didn't go into any detail about the mechanics and
No.
of how that works. I don't know if maybe you can summarize for us what we understand about what the orbital mechanics are that have led to this. This is a collisional process or what? I don't know.
I don't know what you mean with a collisional process.
In other words, have the moons smashed into each other, produced more finer material that have been then transferred to some of the other moons and so on and so forth?
Actually, what the paper describes is purely the dynamical evolution of the ring itself. I mean, the particles in the ring. So it doesn't really touch how it came to be. Or actually, no, I'm wrong. It does talk about the possible collision and what kind of material would be there, mostly Phoebe material rather than the impactor. But then it goes into the dynamics of the dust and what the path and the sizes of the dust, as I mentioned in the talk. Yeah.
Is the Phoebe ring younger than the other rings around Saturn, or is there anything known about how long it will last or when that collision occurred?
Good question. I don't know. Dale, do you know? Anybody knows?
So the lifetime of those particles is much shorter than the solar system, similar to the lifetime of particles in the Jovian ring, which would be thousands to millions of years. So probably the Phoebe ring is not a recent activity, but something that has been continuously supplied by bombardment of the surface of Phoebe.
Thank you. Yeah.
Okay, Cristina, we have a special graphitically encased cup for you, mug for you.
Thank you.
And please join me in thanking Cristina for a great talk.